Yo, chat, the Fent was actually a Microsoft bias spyware that has been slowly and quietly liquefying our brain cells to turn us into droids. The Fent was a sleeper agent that got activated after we logged into Minecraft. Bill Gates has now total mental control over us. Turns out Bill Gates is an intrusive data structure. Now that the Fent is running out, let's talk about intrusive data structure and intrusive interfaces. From what I've read, intrusive interfaces used to be the way to create runtime interfaces, but now using an any opaque pointer is the preferred way. But intrusive data structures are making a comeback, so let's talk about that. Most data structures like arrays, maps, and queues hold the data they operate on. They have ownership of the data. Intrusive data structures, in contrast, don't. They let the data hold the necessary information. The best examples of that are the new implementations of SinglyLinkedList and DoublyLinkedList in the standard library that will be coming in the next version of Zig. If we take a look at SinglyLinkedList, it's a struct with one field which is an optional pointer to the first node of the list. If you want your data to be part of a linked list, you need to add a new field in it of type SinglyLinkedList.node. Then after creating a linked list and your data, you add nodes to the list by either calling the prepend method and giving it a pointer to a node, or by calling insert after on a node directly. Now that we've linked several nodes, we can iterate over the nodes in the list by creating a pointer pointing to the first node and then following the next node. Alright, this is great, but the list has no knowledge of the data. So what's the point of having a linked list if it doesn't have access to the data? Well, that's when the intrusive behavior kicks in. You see, when we add a node inside our data, it's like adding a backdoor inside our struct. Because when you have a pointer to a field of a struct, we can get a pointer to the struct itself by using addFieldParentPointer. So while we traverse our list, we have access to a pointer to the node field of our struct. So we can use addFieldParentPointer to get a pointer to the struct. Once we have this pointer, we can use or modify the data. The way addFieldParentPointer works is pretty straightforward. When you create a struct, the different fields are stored next to each other in memory, and the address of the struct corresponds to the address of its first element. All other fields are stored at some offset from this address. This offset depends on the size and alignment of the different fields, which are known at compile time. So if we know the address of a field and its offset, then we can deduce the address of the struct. But unlike C or C++, Zig doesn't make any guarantee about the memory layout, so unless you're using a packed struct or an extern struct, you shouldn't try to guess the field's order and offset, but instead use addFieldParentPointer or addOffsetOf. Alright, so hopefully this clarified how to use an intrusive linked list. The main benefit of intrusive data structure is that we can avoid unnecessary duplications or allocations, but the data can only be part of a single list, unless we create several node fields. So that was the fun part. Let's see how we can use this knowledge to create an intrusive interface. It's unlikely that you will ever need to do this, but you may see it in the wild, so I want to show it to you anyway. To define an intrusive interface, you start by creating a struct and then add function pointers as fields for each behavior you want the concrete types to implement. These functions must take a pointer to the intrusive interface as a parameter, and you can add additional parameters if you need to. For convenience, you can create methods that calls the functions pointed by these function pointers. Alright, so nothing too complicated here. Now, when you want to implement this interface in a concrete type, you first need to define a field to store the intrusive interface. And then you need to implement functions with the same signatures as the function pointers defined in the interface. Now, this is when it gets a little bit tricky. You see, we have these functions that takes an intrusive interface pointer, but we are not going to give them any arbitrary intrusive interface pointer. We are going to give them a pointer to the concrete types interface field. So if inside these functions we know that we have a pointer to a field, then we can get a pointer to the parent struct using addFieldParentPointer, exactly like we saw previously. So now we have access to any data or method of the concrete type. To use it, we start by defining a concrete type object. We set the interface field to be an intrusive interface object, and we make the function pointers point to the concrete implementations. And we initialize the data too. Then, for example, we can store a pointer to the interface field of the object we've just created, and we can use the methods of the interface just like this. Okay, then of course you are free to make an init function to make this easier. You can also create methods inside your concrete type and then use this method inside the implementations of the interface, like just the usual stuff. Alright. Before I let you go, I want to talk a little bit more about LinkedList. In LinkedList, there's link. And if there's link, Zelda shouldn't be too far away. Yeah, you get it? It's funny because Zelda is a little library that presents a way of creating intrusive linked lists without using add field parent pointer. If we go back to what we saw previously, to make our data part of a linked list, we created a field in a struct to use it as a node in the linked list. Now with Zelda, instead of adding a new field to represent a node, the idea is to turn our struct into a node. So let's take a look at the documentation to see what a SinglyLinkedList node should look like. A node should have a field called next to point to the next node in the list. But the type of the node is the type of our struct T. Or we can use the addThis function instead. A node should also have a bunch of methods to manipulate the list. And this is when the Zelda library steps in. By adding this line, we'll turn our struct into a SinglyLinkedList node and also generate a specialized SinglyLinkedList container. This isn't straightforward, so let me guide you a little bit. We first start by calling the Zelda SinglyLinkedList function, which takes two arguments. The first one is the type of our struct we want to turn into a node, and the second one is the name of the field used to point to the next node in the list. Here, in this function call, the .next is an enum literal, but we can also use a string, because if we take a look at the source code, if we give it an enum literal, it transforms it into a string and stores it into a slice. Otherwise, it just takes a slice of the string. To be honest, I'm not really sure what are the benefits of using an enum literal, so if you know, let me know in the comments. Once it has the name of the field, it calls the function verify field type. That verifies that the field exists and that it's an optional pointer to the concrete type. Okay, so this SinglyLinkedList function returns a type, which is a struct containing useful methods to manage the node, and a SinglyLinkedList type. So this function call returns this struct, which was actually monomorphized with our type T. Then, using namespace brings all the public declarations of this struct inside our T-type namespace. This makes our T-type ready to be used in the linked list. So once we've defined our data like this, we can create a few nodes, create a list, add nodes to it, and iterate over it. The reason why this can be interesting is that you now have access to concrete types, which are easier to use and can make function definitions easier and more readable. Here, with Zelda, it's clear that the function expects a list of T, while it's not with the standard library. And you don't need to use add field parent pointer. Now, the major problem of Zelda is that it uses using namespace. And that's a problem because there's an accepted proposal to remove it. But it doesn't mean it will actually be removed, since people have been known to change their minds. So, I wanted to show you Zelda because I thought it was pretty funny and clever. And I recommend you to read the comments. It's pretty nicely done. Anyway, I've heard that Zig 0.15 should be released in August, and a lot of exciting work is being made. Zig is going to look even better in the following months, and I will definitely make more videos about it. In the meantime, I will make videos about low-level system stuff and experiment new ideas, so if you want to see this, subscribe, or else, bada bim bada boom! Dung dung dung!